In this video, we're going to look at what we know about the insides of atoms, kind of an updated model of the atom. It turns out that John Dalton, with his atomic theory, while it was right about some things, he was wrong about some stuff as well. And mostly it had to do with the idea that an atom is indivisible, that it's the smallest part of matter that there is. It turns out that atoms are made of things that are even smaller yet. One of the tools that was used in this discovery is the cathode ray tube. So the cathode ray tube is just a device that's been evacuated from the inside. There's no air in it, or very little air in it. So you can see in this picture there's a tube, a glass tube. It's hooked up to a air compressor. This device here is an air compressor, and that hose is sucking all the air out of the tube, or most of it. So it's very little gas inside there. And then there's an electrode at the top, just a piece of metal, and another one at the bottom. They're not touching each other. And a guy named Geisler found out that if you set this up and then turned on electrical voltage between the top and bottom, they're called electrodes, there would be a kind of a glow in there. And nobody really knew what this was, what it was. Some people thought that it was some particles. Some people thought it was light inside there. Nobody really had an explanation for it. This guy here, J.J. Thomson, did a series of experiments with a cathode ray tube. And what he did was he took the whole tube and kind of shrunk it down into a small space on one end. And then instead of just having the glow happen inside there, he drilled a hole in one end to let the beam of whatever it was escape. And so then he could get this beam to pass through the rest of this chamber. So he had like an outside room outside of the actual cathode ray tube. And on the end, he painted it with this material. You can see this kind of shiny stuff. And it's like the material that old-fashioned TVs used to be made out of. And when this beam would hit it, it would glow. And then he put a ruler on the end. You can see, almost kind of see a little yellow tape measure on the end. And then he could measure if this moved up or down on the end. He could measure how far the beam moved. And he was just messing around trying to figure out what this was. And he had a hypothesis that the beam was made up of some particles. And that was one of the things that he wanted to test. And he found out that it was. How he knew that it was made of particles was he placed an external magnet. You can see the north and south poles of the magnet. He put a magnetic field around this beam, and when that happened, the beam moved. And that was not known to happen with light, but charged particles would change their path when they were put in a magnetic field. So they knew this from larger particles. So he knew that this stream, this beam was a stream of particles. It wasn't light because of that experiment. He also found out that these charged particles were negatively charged. And he did that by hooking up his battery to a positive and negative plate that were inside of the anteroom, the outside room of his little tube. So remember, he's got this beam going through, straight through here like this, and it's making a spot at the very end like this. And then when he attaches this to positive, let's say, and this plate to negative, those plates inside there, they may have been inside, may have been outside, I don't really know. What would happen is the beam would move towards the positive. So instead of being right at the end of the tube, the beam would bend and he would see his glowing spot on the positive side. So that's the way it would be if it was negative on the bottom, positive on the top. If he switched the polarity so that the positive was on the bottom, well, then it would just bend the other way. So it would bend towards positive, and opposites attract electrically. So that's how he knew that these were negatively charged particles. So that stream and that beam inside there was a stream of very small, negatively charged particles. And J.J. Thomson called those electrons. And he wanted to do some more experiments to find out more about these electrons. So what he did was he measured the force of his magnetic field, and they knew the math behind the force of the magnetic field. That's FH here in this equation. It's the charge of an electron, which he didn't know, but it was the charge on the particle, which he said was the electron. times the velocity of the particle, and then times the size of the magnetic field. So he knew the size of the magnetic field. He did not know the velocity. He had no way of measuring that. And he also didn't know the electrical charge of the electron. But remember, he could make that beam bend with an electric field as well. So he knew the force on a particle in an electrical field was equal to the charge on the particle, that's E, the charge on the electron, which again he doesn't know, times the electrical field. So it's charge on the electron times the size of the electrical field. He knows the size of the electrical field. He does not know the charge of an electron. That's one of the things that he kind of wanted to find. So what he could do is he could balance the force of the magnetism, like this downward force, FH, from the magnet, with the upward force from the charged plates. And if the beam, under the influence of both the magnets and the charged plates, ended up hitting right at the end, well, then he knew that those two were balanced. The force of the magnetic field and the force of the electrical field were the same as each other. Well, since we know that the magnetic field is the charge of an electron times velocity times the magnetic field strength, and he knows that the charge of the electron times the electrical field is the force that the electrical field places on that particle, those two are equal to each other. So what he could do then is E, of course, cancels out, and then that means that the size of the electrical field is equal to the velocity times the size of the magnetic field. And the two things that he can measure are the electrical field and the magnetic field, so that means he could figure out the velocity as a ratio of the electrical field strength divided by the magnetic field strength. Two things that he could measure. Then he thought about the motion of this electron if he took the magnetic field away and just made the path bend because of the electrical plates. And this is a kind of motion that's like projectile motion. So this is the path that the electron takes. These are the velocity vectors. The red one is in the y-axis, let's call it, and the blue one is in the horizontal, or the x-axis. The velocity in the x-axis times the time that it takes to get to the end of the tube would be equal to the displacement in the x direction. Well, he can measure the displacement in the x direction. He kind of knows what the velocity is because he has that in terms of his field strengths. In the other axis, the object isn't moving at a constant speed, it's accelerating. And the equation that gives the displacement, the change in position, so in the y-axis in this case, delta y, in an accelerating situation like this would just be the acceleration divided by 2 times the time it would take to move squared. So he's got an equation that describes the motion in the x-axis and the motion in the y-axis. And he can measure how much the position changes in the y-axis with his little tool on the end. He can measure how much it changes in the x-axis because he knows how big his tube is, how far it is between his plates, beginning and end, because he built the little tube. So he can take this information and using the delta x equation here, and the fact that the velocity, remember, that is the field strength, the electrical field strength divided by the magnetic field strength, he can replace that, so he can say that's E over h times delta t. So then that means that delta t is equal to delta x times h divided by E. So now he has a way of expressing time change for these particles moving through his device. Now, every physicist in his day knew that acceleration is equal to the force on an object divided by the mass of the object. So the mass of the object, well, that's just the mass of an electron. The force, well, remember the force is the electrical field strength force, and that is the charge on the electron times the electrical field strength divided by the mass of the electron. So that means we can substitute this for acceleration. So now the delta y equation becomes charge on the electron times the electrical field strength divided by the mass of the electron, that's all divided by 2 as well, times delta T squared. But we know what delta T is. It's delta X times the magnetic field strength divided by the electrical field strength. So he can substitute that in for delta T. So let's do this up here. This means delta Y equals the charge on the electron times the electrical field strength divided by 2 times the mass of the electron times delta T squared, but that is delta X times the magnetic field strength divided by the electrical field strength. So that's all squared. So delta Y is charge on the electron times the electrical field strength times delta X squared times the magnetic field strength squared divided by 2 times the mass of the electron times the electrical field strength squared. Electrical field strength cancels out to give you that equation. And so now what he realizes is there's only 2 things in here that he doesn't know, that he can't measure. And they are the charge on the electron and the mass of the electron. So there's 2 unknowns in one equation, so he knows he can't find both unknowns, but he knows he can find the ratio of the 2 unknowns. So he takes this equation and he solves it for this ratio. The charge of the electron divided by the mass of the electron, if you solve this equation for that, ends up being 2 times delta Y times E divided by delta X squared times H squared. So E is the electrical field strength, he knows that. Delta Y he can measure by how much his spot moved on his little tape measure. Delta X he knows by how long those electrical plates are. And H he knows that's the magnetic field strength, and he can measure that. So he can now plug in his numbers and find the ratio of electrical charge to the mass of the electron. And what he found out when he plugged all his numbers in here was that it is 1.8 times 10 to the 11th coulombs per kilogram. Now this is a very large number. He suspects the reason this number is very big is because the mass, the denominator of this, is very, very small. So what he does is he proposes a model of the atom that's not a solid sphere like Dalton chose to represent. So these 2 guys, there's a video that you should watch maybe that will help you understand this. They're using something like what's called a plum pudding. This was a British dessert that was popular in J.J. Thomson's time. And basically what it's kind of like is a raisin bran muffin. These guys have a cherry tart, I think is what they have. And there's cherries baked inside of this tart. And there, you can pull an individual cherry out of that tart. And that's what a plum pudding was like. There were bits of plum inside of this pudding, and then you could pull them out. And so Thomson proposed that the atom is really something like this. You have all this positively charged mush inside there. That's what makes up the bulk of the atom. But you had these little tiny bits in there that were negatively charged. Those were the electrons. And that's what all atoms are made of. And he assumed that it was all atoms because it didn't matter which metals he used for his electrodes inside of his cathode ray tube. He would get the same result. It was always the same tiny particle. So electrons were a part of all atoms, and they were smaller than the atom, and they were negatively charged. And that negative charge had to be balanced by this positively charged kind of dough or mush that made up the rest of the atom. That's called the plum pudding model of the atom. This individual, Robert Millikan, worked with his data, with J.J. Thomson's data, to find even more information about the electron. So what he did was he did this experiment called the oil drop experiment. And in this oil drop experiment, he had an atomizer, kind of like a perfume spray bottle with a little bulb on there. And he could spray particles into this can. You're seeing the cutaway version of this can. So this isn't what he would actually see, but this is what was going on inside there. It's like a cutaway. It had 2 plates in it. The top plate had a tiny hole right in the middle, and the bottom plate was solid. And the bottom plate was hooked up to negative charge. The top plate was hooked up to positive charge, so there was an electrical field inside here. Now he would spray these particles in there, and most of them would just land on the top plate, but every once in a while a particle would hit that hole and would start to fall down through here. He's got a microscope here, so he can look inside there and watch close up these particles falling. And as he watches them fall, he can track how fast they're falling and what their terminal velocity is. And he knows a bunch of physics equations, and he can figure out what the mass of these particles, what these droplets are. They're tiny droplets. Okay, so then he's got an X-ray source here. This X-ray blasts a bunch of energy at the air particles that are inside of this can and knocks electrons off of them. And those extra electrons then stick to these oil droplets and make them into charged particles. So then he takes the electrical field and messes around with it until he gets the electrical field just big enough to balance the gravity pull that's making the particles sink to the bottom of his can. So the electrical field is now balanced with gravity. Well, the gravitational force, every physicist, including Millikan, knew, was mass times the gravitational field strength of the Earth. And the electrical field strength, well, remember, that's equal to the charge of the particle times the electrical field. That's the same formula that J.J. Thomson used, except this Q is the charge on the droplet. It's not the charge of an electron, because this droplet, he's assuming, has a few, maybe one or more electrons attached to it that got knocked onto it from the air particles by the X-rays. But these are balanced because he makes his field such that the electrical field balances the gravity and the drop is just suspended in space. It's not moving. So because they're equal, then he can say that the charge on the droplet times the electrical field strength, which is something he can measure, is equal to the mass of the droplet times the gravitational field strength. Okay, so he can measure that because he knows how fast it's been falling and what its terminal velocity is. Everybody knows the gravitational field strength, it's a common number. The electrical field strength he can measure, so he can solve this and find the charge on his droplet. It's the mass of the droplet times the gravitational field strength divided by the electrical field strength. And he does a bunch of trials, like many trials, and gathers a lot of data, and here's what he finds. Here's a sample of his data table. There are lots more of these. The important thing to look at is what's the difference in charge from droplet to droplet to droplet. And if you look at these numbers, they all are whole number multiples of about 1.6 times 10 to the negative 19th. What's going on here is he's finding that, first of all, they're all multiples of the same number, 1.602 times 10 to the negative 19th. And also he finds that there is never a number smaller than that, never a difference smaller than that. So he assumes that the smallest unit of charge that there is 1.6 times 10 to the negative 19th. And because the difference between these droplets is the difference in whole numbers of electrons, he says that must be the charge of one electron. Okay, so now he knows the charge of an electron. This is in coulombs. So he can use the ratio that Thomson got to find the mass of the electron. So 1.6 times 10 to the negative 19th coulombs. And Thomson had found out that 1.8 times 10 to the 11th coulombs per kilogram was the charge to mass ratio. Using dimensional analysis, you can get coulombs to cancel, and this will give you the weight of an electron in kilograms. And if you do the math, it's 8.9 times 10 to the negative 31st kilograms. That's a very tiny number. That's, a zero at, a decimal point, and then 30 zeros, and then approximately a 9. So it's very small. That's the mass of an electron. So one of the next things that happened was they discovered some more things about the internal structure of the atom. This guy, Ernest Rutherford, who was connected to J.J. Thomson, I believe he was his student at one point, was experimenting with this source of particles that came from this radioactive material. And the things that he knew about these particles was that they were positively charged, and compared with an electron, they were very heavy. And that's pretty much what he knew. And he was just experimenting with them, trying to find out more about them. And he set up this experiment that we have in this picture. In the middle is a sheet of gold foil, and he chose gold because he could pound it really, really, really thin, so it was just a few atoms thick. And that way he could try to get at, as close as he could, how individual atoms would interact with these particles. And then he wrapped it with a sheet of material that when charged particles hit it, it would make a little bit of a spark. And then he was just looking for where the sparks were to try and get some clue about how these things would behave when they encountered atoms. What he expected to see was just a lot of sparks pretty much on the opposite side of the gold foil. He thought there might be a little bit of deviation, but he had acceptance of the plum pudding model of the atom, and he thought that mostly it was this positively charged, not very dense mush, and then these teeny tiny electrons scattered throughout it. And so he thought his particles, his alpha particles they were called, would just go bombing straight through the atoms of gold and just end up on the other side. And that's why he expected to see lots of sparks here when he did his experiment. What he actually saw was quite different. He did find a lot of sparks on the opposite side, but he's found sparks pretty much randomly all over the place, including some that were even back behind the gold foil, which kind of indicated that these alpha particles were bouncing off something and being returned back to the direction that they came from. And that did not support the plum pudding model of the atom, and so a new model of the atom was needed. So this is what Rutherford came up with. Instead of the atom being electrons in this not very dense positively charged mush, he thought all the positive charge was concentrated in the middle of the atom in a thing he called the nucleus that was positively charged and fairly dense. And so what was happening was these alpha particles were coming up to these heavy nucleuses, and bouncing off of them because they were repelled by them because they were positively charged, but also because they were quite heavy. And that's how he could explain some particles being deflected off to the side or even deflected backwards. So this is the model that Rutherford proposed for the atom, that the electrons are in orbits that are somewhere on the outside of the atom, spinning around in these kind of circular, some shape orbits. They didn't know too much about that, but they figured they were on the outside. The atom is mostly empty space, but then in the middle is this pretty dense, positively charged nucleus. And so as the alpha particles are going through the gold, they're encountering atoms that are like this, and so some of them are just going to go straight through. Lots of them would be, and that's why he did see a lot of sparks on the other side of the source, but then every once in a while one would hit and get bounced back or deflected off to the side because these are positively charged, and the alpha particles are also positively charged. So they're not going to stick to each other, they're going to be repelled, and they're going to bounce off this relatively dense thing. Later on, some other people were doing more work, and they discovered that the nucleus was actually not made out of one single particle of varying charges. Depending on how many electrons were there, there was an equal number of what they called protons, positively charged particles. They're bigger than electrons, but they have the same charge, only positive instead of negative, the same size of a charge, that 1.6 times 10 to the negative 19th coulombs, but positive. Now, that's a little bit of a problem because you have all these positively charged things all compacted together in the nucleus. That's not going to happen because they're all positively charged. They're going to repel each other, and the whole nucleus would explode. So they knew that something else had to be going on here. And some people were starting to understand that there was another force called the strong force that attracted all kinds of particles to each other, no matter what their charge was. But it didn't act over a very large distance. So it was very strong, but short acting. So what they could use to kind of rectify their model of all these protons having to be close to each other was they determined that another kind of particle also made up the mass of the nucleus, and it was called a neutron, and that's represented by the little blue spheres in this model here, this picture. They don't have any charge at all, but because all particles are attracted by the strong force would attract them to each other, and also the protons to them and the protons to each other. So as long as the nucleus was small enough for that strong but short-acting force, all these protons would stick together by the strong force, and that would overcome the repulsion of positive for positive that would otherwise cause the nucleus to explode. Now, if the nucleus gets too big, then the strong force can't act over that big of a distance, and the nucleus will start to fragment. It will start to break into pieces. And in fact, that is what happens with larger atoms that have larger nuclei, like uranium or plutonium. The nuclei are so big that the strong force can't always keep it all together, and sometimes they split off into smaller fragments. And in fact, that's where the alpha particles were coming from that Rutherford was using in his original experiment. They were just pieces of nuclei that were breaking off of nuclei that were too large. So this is the current model of the atom. The electrons are somewhere in the outside. Where they are, that's a topic for another unit in this class. But they're somewhere in the outside, and the nucleus is made up of protons and neutrons. That's where all the positive charge is located, and that's also where most of the mass for the atom is.